Okay, we have been spending some time working with the Schrödinger equation, various forms of the potential, and we saw various types of solutions, etc. But now it's time to perhaps look at a more complete picture of quantum mechanics. So during these first 2 hours, we'll have some discussion of the mathematics associated with quantum mechanics, and we'll just tie some loose ends and continue from there. Okay, so we'll also introduce new notation and such stuff. So this is the chapter with the title Formalism in Griffiths. So we'll just work on the mathematics of this for a while. Okay, so what do we have? Okay, so we have a set of objects which we call the wave functions, and then we also have operators. Okay, so we have these wave functions. I'll use the letters F and G for them. Okay, so we have some wave function f, and then we have an operator which operates on this function. It's a complex function, okay, which gives us another wave function. Okay, and we have been doing some operations with them. Okay, we find expectations value of the operator and such things. Okay, but we'll now look at some properties of these operators. Okay, so in particular, if we take an operator relation which looks like f star q g, so these are all functions of x, okay, dx. Now, I can define a different version of this operator. Okay, it's going to be something which looks like, okay, so this q, instead of operating on g, will operate on the left-hand side, okay, the complex conjugate, and g dx. Okay, so this is not always true. Not all operators will do it, but we define a Q dagger operator which satisfies this equality. Okay, so for every operator Q, we try to find a Q dagger operator, okay, which is going to be the Hermitian adjoint of the operator Q, okay? Now, sometimes this is written, okay, it's the right-hand side, you'll see written as the complex conjugate of this quantity, so it's going to be G star, okay, the complex conjugate of this is going to be G star Q dagger F, okay, dx, the whole thing complex conjugate, obviously. The two are equal to one another, okay? Now, the special case is when Q equals Q dagger, okay? Then, okay, Q is called a Hermitian operator, Okay, so our favorite operators that we use, things like position and momentum, are all Hermitian operators. Let's just check. Okay, so as an example, okay, suppose I just write such an equation: F star x g dx, okay, is equal to, you see, I can always move this x to the left. Okay, so it's going to be x, and it's real, so I can easily take the complex conjugate, okay, g dx, right? So if this is q, okay, this is q dagger. So in this case, q and q dagger are the same. So that means x is Hermitian. Okay, let's do another example. Let's see the momentum operator. So suppose I have F star P G dx. What's that going to be equal to? It's going to be F star H bar or I, okay, and the dx G dx. But now I have this nice procedure that I can apply whenever I have a derivative inside these integrals. I can do my integration by parts, which what it does is it moves the derivative from g to f, okay, but I get a minus sign because of the integration by parts, okay, so I'm going to get minus, okay, let me put the h bar over I out, d f star dx g dx, right? But now I can place this h bar over I inside the complex conjugate. So I can write it as, okay, h bar over I without the minus sign now, because they can evaluate a complex conjugate. So that's del star f star g dx. Okay, so let me just finish this. This is going to be p f complex conjugate g dx. Yes?
Also, for the hi f conjugate multiplied by g conjugate term goes to 0, right?
Yes, okay. In all of these integration by parts that we do in quantum mechanics, if these stuff are things like wave functions, they go to 0 at infinity. Okay? So that's why we do not put the boundary terms. The boundary terms are always equal to 0. Okay, so I have that. And now you see, according to our definition of the Hermitian adjoint, okay, this thing which is in front of F is going to be P dagger, which is equal to P. So that means P is Hermitian. So okay, you can just go through certain relations which are relatively trivial. If you have, for example, two objects, A and B, okay, two operators like this, if you want to obtain the adjoint of that, it gives you, okay, A adjoint plus B adjoint. If you have a number, okay, so if you have something like C times A adjoint, you can pretty easily see what that's going to do. Okay, that's going to give you C complex conjugate times A adjoint, because that will end up in this complex conjugate with a conjugation of the constant. What else? Let's just work out something like what is the adjoint of product of two operators. Okay, so what is, for example, A, B, two operators adjoint? What is it equal to? Okay, so let's just look at that. So what I have is some F star A, B, G, dx. Now I want to move these operators one by one, okay, to operate on F, okay, towards the left, so that I obtain my relationship. So how do I do that? Well, I can take this B times G as my right-hand function, okay, and think of A as an operator all by itself. So what does that give me? That gives me, okay, this A operating on F, okay, but with an adjoint, complex conjugate, times B times G dx. But now I can look at this operator, okay, and this is my new left-hand side. So now I can move that into the left-hand side, and I'm going to get integral, okay, adjoint of B acting on the left-hand side, A dagger F complex conjugate G, okay, dx. So this term here now, you see from our definition of the adjoint, is the adjoint of A times B, right? Okay. So A times B adjoint is going to be B adjoint A adjoint. Okay. So we have these properties. Okay, why are we going through this process of being Hermitian or not, and whatnot? But we'll see that Hermitian operators are important for physics. Okay. Now we have already introduced the concept of the average S. All right. So we have discussed the concept of the expectation value, or the average value. Okay. And that was something like psi star q psi dx, right? So we call this the expectation value of operator q with respect to the wave function psi. So it will have different expectation values for different psi's. Okay. Now what I can do is, okay, I can see what this is going to give me for a Hermitian operator. Okay, I had my equation somewhere over there, but let me put it up here. So my definition for the Hermitian adjoint was F Q G dx is equal to, okay, the everything in the opposite direction, G star and Q dagger F dx, but the whole thing complex conjugated. Okay. So let me do the following. Let me take the complex conjugate of both sides of this equation. Okay, so I'll write the complex conjugate, but while I am writing the complex conjugate, okay, I'll also use this form. Okay, so I'll go from this form to that form. Okay, so this is going to give me, okay, F and G are the same in these cases, so it's going to be psi star again. And then I'm going to get Q dagger psi dx. You see I get almost the same form except that I have the adjoint. Now, if this is a Hermitian operator, then this is going to be psi star Q psi dx. Okay, so if Q is equal to Q dagger. So if Q is Hermitian, okay, put your phones away. Okay, so if this is Hermitian, then you see this is equal to that, and the right-hand side is going to be Q psi again. So this says that this object, whose complex conjugate is equal to obviously this thing here, so it's equal to its complex conjugate, which means that the expectation value is real. Okay, so maybe we should start making a table of properties of these Hermitian operators. Okay, so expectation value of Q is real, okay, if Q equals Q dagger. Okay, Q equals Q dagger means, okay, the operator is Hermitian. Times it. Okay. Let's move on to other stuff. What else? Let's look at the eigenvalues. Eigenvalues and eigenvectors of Q. Right? So we know how that works. If I have an operator Q and it's going to have a number of eigenvectors, let's call them Fn, and there's going to be corresponding eigenvalues. Okay, so these are the eigenvectors. Maybe I should call them eigenfunctions. Okay, they are eigenvectors in some sense, which we'll see, but at this point it's better to call them eigenfunctions. And I have something like this. Okay, so if I now look at the expectation value of this in any one of these states, so if I just look at Fn star Q Fn dx, okay, what do I get? I get Q times Fn is lambda times Fn, so I'm going to get lambda n Fn star Fn dx. Okay. Now this part is real, and if Q is Hermitian, I know that this whole thing has to be real, okay? Because now this thing is the expectation value of Q with respect to the nth eigenstate. So since I know that all expectation values are real, then this expectation value must be real, which implies that lambda n, okay, are all real. Okay, so this says that, okay, if, again, if q equals q dagger. Okay, so let me just, I'm writing these properties. I'll just assume that anything that I write to the right-hand side of the board is, okay, for Hermitian operators. Okay, for Hermitian q, expectation value of q is real with respect to any wave function, but I also have, okay, eigenvalues are real. Let's look at some other properties. Let's look at something like what happens if I have fm star q fn dx. Okay. So again, same sort of stuff. This just operates on fn. So I'm going to get fm star. Let me squeeze the lamb down over here. Fn dx. Right? But now let me write down, okay, using my adjoint equation. I know that this is going to be equal to, right, q operating towards the left on the function on the left, fm star. Normally I would put in a q adjoint, but this is a Hermitian operator, times fn dx. So this time q is operating on fm, the other eigenfunction. So I'm going to get lambda m. Okay, so this is going to be lambda m times, okay, fm star fn dx. Okay, now let me just subtract these two equations from one another. I know that the left-hand sides are equal. So the left-hand side is going to give me 0. And the right-hand side is going to give me lambda m minus lambda n. Okay, fm fn dx. So if lambda m is not equal to lambda n, okay, so if lambda m is not equal to lambda n, that implies that this fm fn, okay, is proportional to delta mn. Okay, so they have to be 0 unless the eigenvalues are equal. You see, if the eigenvalue, if I do this for two objects, two f and n, which have the same eigenvalues, that's called a degenerate case. We have not, okay, come across very many cases like that. But if there is degeneracy, if lambda n is equal to lambda n, you can still go through this process by a method known as what? Gram-Schmidt. Okay. Have non-mathematicians seen this? Do you know what Gram-Schmidt orthogonalization is? Okay. So you can use the Gram-Schmidt orthogonalization process to orthogonalize that stuff also, so that for the general case we can say that the eigenvectors are orthogonal, and of course you can always normalize them so that they are orthonormal. Okay, so we'll always assume that, well, okay, we'll always assume that the stuff fn star fm dx is equal to delta nm. Okay, so this then holds for any Hermitian operator. So it shouldn't be surprising at this point that we are looking at all these problems in which we are using these physical operators. And what operators have we been using? Well, the Schrödinger equation, okay, is made up of p squared over 2m. Okay, so the operators we have been using are what? We have the kinetic energy operator, which is p squared over 2m. Okay, is this Hermitian?
Yes.
Yes, right, because it's just p times p, and its adjoint is going to be p dagger, so it's going to be p squared again. Okay, so it's Hermitian. It contains a v of x, which is the potential energy. Okay.
It's Hermitian because it's real values.
Okay, so it's Hermitian because it just contains the x, and the x operator is Hermitian, x and powers of x, right? So that's that. Okay, so momentum we have used. Yes.
If potential wasn't real but it had imaginary part, then it would not have been self-adjoint.
Yes, fortunately we have no imaginary potentials, okay? Everything we use is real. Okay, then if we have, okay, what else? So at this point you might think almost everything is Hermitian, but we did use the operators, for example, for the harmonic oscillator, A plus. So what did that look like? It looked like x0, well, x over x0 minus I p over p0. Now, is this Hermitian?
No.
No, okay, because of this I. Because x is Hermitian, p is Hermitian, but I is not. In fact, if you look at a dagger, a plus dagger, so sorry for the notation, this is plus, a plus, it's the raising operator in harmonic oscillator, and this is dagger. It's not really plus, but if you look at your textbook carefully, you see that it's a type of knife that Macbeth uses to kill lots of people, okay? So it's a dagger is x over x0, I goes to plus I, p over p0, so this is a minus, okay? So these two operators are not Hermitian, they are adjoints of one another. All right, but on the other hand, A plus, A minus, you'll remember that, that's a number operator. Is that Hermitian? Okay, this is Hermitian because we changed the order. Okay, so it's going to be A minus adjoint, A plus adjoint, so it's going to back into itself. So this one, for example, has real eigenvalues again, right? It's the number operator. It picks out the energy level number. Okay, so it's not surprising that we have been working with eigenfunctions which are all orthogonal to one another, no matter which potential we use, and also that all the eigenvalues turn out to be real. Okay. Any questions? Any comments? Yes.
So the eigenfunctions are orthogonal.
Yes.
Should this integral equal to sigma integral or proportional to sigma integral?
Sigma, what's the sigma there? Delta. Okay, no, you see, the eigenvalues are orthogonal, which means this is going to be proportional to that, but you can always normalize these things, okay? So normalization is something that you can always do, okay? So we'll assume, by assumption I mean that someone has taken the time to normalize them, okay? So they are all normalized, and when we say eigenfunctions of this operator, we'll, okay, under almost all conditions, assume that they have been normalized, okay? So that we don't have to worry about normalization. All right, what else? Let's see. All right. So we have these properties for the eigenfunctions. Let's just look at expectation values with respect to those eigenfunctions. All right. So this is all stuff that we have been doing, okay? Except that we are now doing it in a more general way for general types of operators. So I have these orthonormal eigenfunctions, and I can take my arbitrary wave function, psi of x, and I can expand my function in terms of them. How do I do it? Okay, I can use this orthonormality procedure and just multiply both sides of this equation by the complex conjugate of one of these things. So if I just multiply the left-hand side by f star m of x, psi of x dx. On the right-hand side, I'm going to get n cn fn of x, fm star of x, fn of x dx. We just said that we are going to choose these things as orthonormal, okay? And that means all terms here except the nth term will be 0, and I get my CMs. That's very nice, okay? It gives me a way of expanding everything in terms of that. Now, what will I then, how is this going to be useful? Well, let's first look at the expectation value of the operator with respect to its eigenfunctions. Okay, so what is the expectation value of Q with respect to any one of these eigenfunctions? Okay, so let's just do the algebra. Very simple. Fn star Q Fn dx. Okay, this we did earlier. This is just lambda n, right? So it's going to give me lambda n times 1, and I have then determined what Qfn is. But now I can do the same thing for Q squared. In fact, it's just very trivial. So if I have Q squared Fn dx, I'm just going to get lambda squared n. So I'll get lambda n squared. What does that mean? If I now look at the fluctuation in Q for that state, let me look at fluctuation of Q squared. Okay, it's going to be the average value of Q squared minus average Q squared. So it's just going to be 0. Okay, so eigenfunctions of an operator, let me just quickly go back to my table of, table of facts. Okay, so eigenfunctions of Q, okay, represent,
Energizing state.
okay, definite, okay, value states for the operator. Okay, so what you mean by that is that delta Q for that state is going to be 0. So those are states with definite values of our expectation value. Okay, so you see this thing building up step by step into showing that these Hermitian operators are special and useful for our purposes. So what we'll do, okay, is to actually postulate, okay, every measurement in quantum mechanics is associated with a Hermitian operator. Okay, so anything that you can think of, any physical measurement, momentum, position, okay, energy, potential energy, whatever, each one of them corresponds to a Hermitian operator. The eigenvalues, okay, are possible values of the measurement. Okay. And eigenstates okay, states with definite okay, results. So normally measurements, okay, are going to be random. I'm going to get random results depending on what the eigenvalues are. So sometimes I'll get one eigenvalue, sometimes I'm going to get some other eigenvalue for a general psi, but for the case of the eigenstates, those are states with definite value of the measurement. Okay, for those things, there's no okay, there's no uncertainty. All right, now let's return back to our expansion problem. We have expanded a general wave function in terms of okay, we have expanded our general wave function in terms of the eigenstates. So let me return back to that. I have psi of x is equal to Cn Fn of x, okay, summed over n. And I know how to determine these Cn's, okay, but let's see what now those Cn's mean. First of all, let's just see what is going on with the normalization. So psi star of x, psi of x dx is something that I normalize so that it's always equal to 1, okay, because the probable density. So that I have to do on the right-hand side. So I have to multiply two series. So I need two indices, n and m. So Cn star Fn of x, Cm Fm of x. And I have to integrate this, okay, dx. And this Fn Fm integral, I know gives me delta and m. Okay, so if I put that in, this means all terms here will be 0 except when n is equal to m. So I'm going to get Cn star Cn summed over n, okay, which is just the magnitude squared of the Cn's. Okay, so remember why we are normalizing this. We are interpreting this psi as a probability density, okay, in terms of the variable x, so that if I integrate it over all space, I have to get 1. On the other hand, here I have, again, something which adds up to 1, and I'm going to interpret this also as probability, this time corresponding to the nth state. Okay? So Cn magnitude squared is going to be the probability, okay, of being in that nth state. Okay, so maybe I'll extend my table over here on the right-hand side to say that Cn magnitude squared is the probability of, okay, measurement resulting in lambda n. Okay, so let's go back. In fact, let's see what the expectation value of q for this psi state is going to be. It's going to be psi star q psi dx. So I'll do the same thing over here. Integral, again, I have two series, one for psi star, one for psi. So I get Cn star Fn star of x, q Cm Fm of x dx. But q operating on Fm is just lambda m times Fm, right? It's just eigenvector. And then I have this Fn star Fm term, integral, which is going to give me delta Nm. So I am doing this a little quickly, but by now I'm sure you are also fluent in this. So this is going to pick out the n equal to m term here, and that is going to give me a simple series, Cn magnitude squared, Cn star, times lambda m, lambda n, okay, same index. So you see, this is the interpretation of this is just some Pn lambda n, okay, very consistent with our expectation value of psi type of interpretation. The probability of getting lambda n is Pn, okay, and therefore Pn times lambda n just gives me on the average what lambda n is. Okay, any questions? Yes.
Here, in this part where we wrote Cn star Cn, why didn't we write Cn star Cn?
Because if n and m are different, the term is 0.
Oh,
Okay? So this delta Nm picks out only those terms for which n is equal to m. Okay, so that removes one of the summations. So whenever you have a delta function like this, if it's under a summation, you remove one of the summations and put n equal to m. If it's a Dirac delta function, again, in that case, you remove the integral and put in, replace one variable with the other. Okay? All right. Now, in all of these expressions, okay, I have used these summations. So all of these things correspond to system which has a discrete set of eigenvalues and discrete set of eigenfunctions. Okay, so these are, for example, these eigenfunctions we have seen in the case of the harmonic oscillator or particle in a box. Okay, in those cases we had these energy levels which were all discrete and we did sums over them. But not all operators have a discrete spectrum. Okay, so this is called a spectrum. Some operators have continuous spectra, right? Okay, such as momentum. Okay, so it doesn't even have to be a free particle. Now we are just talking about operators. We are not discussing, you see, our discussion here now is independent of the Hamiltonian. We just are working just with the operators themselves. So what we are going to do next is to look at operators with continuous spectrum. Now, you see, in that case, we have to be somewhat careful because here I proved for you certain relations, right? I, for example, said, okay, this thing has to be real, or that this object has to be delta and m for different values of the eigenvalue. In all of these discussions, we assume that these integrals existed. Okay? Now, for eigenfunctions which extend to infinity, such as the case of the momentum, and as you'll see, the position operators, these things extend from minus infinity to plus infinity, and you cannot really talk about these integrals because they do not converge. Okay? But what you can do, which we will not do at this stage, is that you can assume a finite amount of space. Okay, you say, okay, my space extends from minus L to plus L. So assume that space is like a, okay, particle in a box type of thing, extending from minus L to plus L. And in that case, obviously, all of these things work very nicely. And then you take the limit L going to infinity. Okay? And everything works out, falls into place very nicely. Okay? So I'm not going to go into that detail, but I'll just talk about the results for the case when we have a continuous spectrum. Okay, so it's a good place to stop. Let's have our break. We'll go on.